I've been thinking a lot for the last 25 years about the question of what sorts of network structures should be used in different applications. First, I thought about this in the realm of parallel computing back when I was a PhD student, and more recently I've been thinking about the same topic but now in the context of data center networks. Here's a little picture that I really love of a row of racks of servers in a Google data center. And you can see here in this one row there are hundreds of servers, and Google and Microsoft and a few other companies are building data centers where you have thousands to tens of thousands to even perhaps hundreds of thousands of servers within the same facility. And these servers have to be connected somehow. And so perhaps not surprisingly, a cottage industry has been spawned in the networking research community in which different groups will propose, my network is better than your network. And there's a lot of interesting designs here. And I don't want to put down a cottage industry because I was part of the same cottage industry in the late 80s and 90s. We were doing the same kind of thing for parallel computing. But also we eventually learned some lessons about how to think about networks sort of at a higher level or from a different point of view than the fine details of the structure. And I'm going to explain what I mean by that as we go along. Let me give you a couple examples of two of these types of networks. This is a figure from the paper that was first on my list. The authors called this network a fat tree, and it is indeed a fat tree. And the idea is that you have a group of servers within a rack connected to a top of rack switch, and then there are several other layers in this network. And the way that you send a message from one server to another is you sort of route a path up to the least common ancestor, and then you go back down. And one technique that people have proposed for load balancing is on the way up, you take a random path when you have multiple choices, and then on the way down, there's a unique path to the destination. This turns out to be a special case fat tree in which the total number of wires shown at each of the three levels is equal. So we would call that a full bandwidth fat tree, or we would call that a network with an oversubscription ratio of 1. Okay, if the oversubscription ratio is higher, it means that there would be somewhere in the network where the capacity was less than the total capacity used to connect the servers directly to the network. This particular fat tree also is almost identical to a butterfly network. And the only reason it's not identical to a butterfly network is that at the top level of the tree, instead of having two edges going down and two edges going up at each switch, they used the 4 ports and pointed them all down. But if you'd had 8 switches at the top and had 2 edges up and 2 edges down, you'd have a butterfly network. Here's another really very different looking network that was proposed by Brighton Godfrey and Kit Singla, maybe some co-authors, called a jellyfish network. And their idea was to have a network where the degree of each node was fixed, but the connections were chosen randomly. And random graphs have a lot of nice properties, one of which is that a random graph has some chance of being an expander graph, which means that each subset of vertices is guaranteed to have a large set of neighbors. And they compared the performance of this network on various benchmarks with a network they called a fat tree. But if you look at the actual structure of their fat tree, it really was identical to a butterfly network. So it was, again, a sort of a special case fat tree that's a full bandwidth over subscription ratio 1 fat tree. Now, there are a lot of people who are queasy about the idea of really implementing a randomly wired network in practice. And one of them just walked into the room and sat down. So I want to show you a picture I found on a website called IT Disasters. Okay? This is what it would look like, I'm afraid, if you tried to build a jellyfish. And what I found most hilarious about this web page is they had a commentary where people could put in their comments. And they were all complaining. You know what they were complaining about? Not this horrible spaghetti mess. They're like, I can't believe you used all yellow. Yeah, so, but there's a serious point here, and that is, and this, we're going to come back to this, but two things. One is packaging really matters, okay? In practice, figuring out how you're going to route the cables and wires really matters. And the second point is that if you build a network where the connections are chosen randomly, the average connection goes halfway across the data center, okay? These are all long wires. So that's a problem, both in terms of cost and packaging. Now, one of the reasons why there are so many competing designs for networks is that there's so many different ways in which you could measure or characterize a network and then compare them. So, all of these different measures here have, in certain applications, they matter. So you might ask, what's the bisection width of the network? Like how much data can I route in bulk? Or what's the diameter? Maybe I care about having very short paths between nodes because I've got a latency bound application. Or what's the maximum degree? Is this going to be hard to physically realize, et cetera, et cetera? How big a space do I need for this network? This is part of the reason why it's very hard for anyone to say, you know, my network's the best, because someone else will say, well, but mine's better on one of these measures. So I want to propose something else. I want to propose that you should try to build a network that is competitive for any application, even though you don't know what applications might be run on it in advance, with any other network that can be built at the same cost, same amount of money. All right, so it's forget about necessarily looking at specific combinatorial properties of the network. I want you to look at what it can actually do. Now, it's not clear that you can do this. You might say, well, that's crazy. If I know my application in advance, I could build a special purpose network, and I'm going to get better performance than some generic network that Bruce is proposing here. It sounds like it might be impossible, but there's some hope that you might be able to do this. And this is based on the theory of area and volume universal networks that was developed by my thesis advisor, Charles Lyserson, back in the 80s. And what Charles showed is that in his first paper, there's a fat tree network of area n that can emulate any other network that can be laid out in area n with slowdown at most polylogarithmic. And then this theorem was refined over time to get the slowdown to log n. And the notion of area, universality, and volume, it can be generalized to 3 dimensions if you had a 3D VLSI layout technique. And so at least in the context where slowdown means how much more time it takes to perform some computation, okay? Or another way to say this is what he directly showed was if you look at sort of 1 unit of time in which the original network was moving data, within log n or time, the fat tree could do the same thing. Okay? And log n is sort of the height of the tree. So what Charles showed was that at least in the context where cost is measured in terms of area or volume of a layout, there is such a thing as a universal network. Okay, now This talk is going to be about the more complicated setting in which there isn't some uniform medium and some simple metric of cost, where it's a mess, but we have to think about real dollars and things you can spend real dollars on. And yet we still want to prove an analogous type of theorem, or at least suggest an analogous type of approach. So let me tell you a little bit about how I think about fat trees and how Charles thought about fat trees. And the idea is that there's two structures to a fat tree. There's a coarse structure, which is just some kind of perhaps a regular tree. Here I've shown a regular four-ary tree, and there are nodes in this tree. There are channels in the tree. The channels can have differing communication capacities. So typically the channels would get more and more capacity as you moved up from the leaves to the root. And the leaves here you can think of as, representing, in the old days we thought of them as processors, but in a data center those are servers. Now, there are a lot of different fat trees, and the primary way they differ is in how much capacity you put at the channels. And what we'll see is that for area universal fat trees, they were not full bisection, full bandwidth trees. You don't, the total amount of wires here or capacity at each level is not the same. It changes as you go up the tree, it decreases. Now, given a coarse structure, then there's some way to realize it as a fine structure where you actually replace those sort of supernodes with individual switches. And so here what I've done is I've using switches with 2 links going up and 4 links going down, I instantiated that coarse structure. So those 4 nodes at the top, those which are like switches, those represent that one supernode I showed you before. And there are 4 channels, and each of the channels going down has capacity 4. And then this is a supernode, and then you have capacity 2 to each of these servers and so on. And this type of fat tree was, I think Ron Greenberg in his thesis calls it a butterfly fat tree. But notice that it's not isomorphic to a butterfly anymore because the capacities are going down as you go up to the root. So I'm going to give you like a 30-second proof of why there is an area universal fat tree. And here's how it works. Somebody says, here's my network, and it can be laid out in area N. And what you do is you say, okay, it turns out you can assume it's a square layout without loss of generality, so that's not a problem. You say, what I'm going to do is I'm going to take your layout of your network, and I'm going to cut it. I'm going to cut the layout. And I'm going to do it, the reason I picked a 4-ary tree, that's a nice thing for a 2-dimensional layout. I'm going to cut this thing into quarters. And I'm going to look at, when I cut it, how many wires were cut. And it turns out for each of these quarters, the maximum number of wires that can be cut is square root of n. Okay? And so that's going to be the channel capacity at the root of the fat tree. And then we're going to recurse. And so you get a fat tree network where at the root, at the leaves you have n leaves basically, but at the root you only have channel capacity square root of n. And you can lay out the fat tree. It looks something like this. And the basic idea is that each of these subtrees is going to take care of whatever communication would have gone on in the network we're trying to emulate locally, and only when communication has to pass between the quadrants of that original network do we go up to the root. Right? So this by the way is this is like again I'm using switches with four edges going down and 2 edges going up. Right? So that's sort of what an area universal fat tree looks like. And by the way, don't get the wrong impression, okay? This is not a talk in which I'm saying data centers should be built as fat trees. Fat trees are just one example of the approach to cost universality that I'm pushing, okay? I don't care how you do it. If you can show me that for a fixed amount of money, your network can emulate any other network that costs the same amount of money, that's fine with me. I don't know any ways to do it that aren't kind of close to this, But the goal isn't necessarily to push one particular network topology. I want to say one more thing, and that is that despite my kind of making fun of the layout of that random graph or an expander graph, I think there may be interesting places to include components within a network that have expansion properties or irregular wiring. And one thing you can do in a fat tree is you can say, well, when it comes to implementing a channel, I could have some redundant edges. So all the fat trees I showed you already have the property that there are multiple choices on the way up. But the ones I showed you so far, there's only one choice on the way down. Here what I've done is I've added redundant edges. So from this node to get into this quarter, I've now got two choices. And you could, once you start throwing in multiple edges, you can make each of these channels a bipartite expander. And in fact, in Charles's original paper, he used a construction here called a concentrator that's very closely related to an expander. And the advantage of this is that now on the down path you've got redundancy, and so it's particularly useful if you want to deal with fault tolerance, right? You can work your way around faults both up and down. And of course, doing this doesn't hurt. It only adds constant factor to the layout. It doesn't change the universality theorems. But you can start proving new things about fault tolerance and deterministic adaptive routing algorithms once you have expansion in the channels. So Charles, though, at the time, he knew that we weren't going to be building really large-scale networks on a single VLSI chip. And he was deeply involved in the design of the connection machine CM5 network, which was a type of fat tree. And he started thinking about how do you extend this approach to networks that are not constructed in a single, planar physical medium. And he said, in practice, there's no simple mathematical rule that governs how you should set these channel capacities. Instead, what you need to do is look at the actual technology that's available to you to build your network and match the channel capacities to what the technology can provide. So this means in the data center context, we want to think about, okay, well, look at what can be done connecting the servers within a rack, and what can be done connecting servers within a row of racks, and what can be done across rows of racks, and figure out what's practical and cost-effective at each sort of level of packaging technology. All right? So here in a nutshell is the way you translate the old theory of area and volume universality into this new one that's based directly on dollars. Here's a proposal for building a universal data center network. What you do is you build a hierarchical network with a small number of layers, and then you spend an equal amount of money on each layer of the network. Okay, so it's equal amount of money across the whole data center, connecting the servers within a rack, connecting servers that were within the same row, and then maybe connecting servers that are in different rows. Or maybe you have two levels of that, but it doesn't matter. And the claim is that this network will be universal in the following sense. If somebody comes along and says, you know what, I built a better network, it's doing better on some application, then I'll say, well, okay, fine. You built your network inside some data center, and what I'm going to do is I'm going to claim that your network, I can do this same kind of decomposition where I sort of go into the data center and say, okay, I'm going to cut the building in half and cut it this way. Don't worry, if you're from Microsoft or Google, this is a thought experiment. We're not going to actually cut the building in half. And I'm going to look at, okay, well, in your network, how much money did you spend on the wires that are crossing these partitions I made in the building? Well, I spent a quarter as much as you did, basically. Okay, not as much, but it means, I'm competitive still. Yeah.
This notion of allocating the same amount of money doesn't seem constructive, because money doesn't tell me what network to build. Because
no, but I'm telling you, I'm giving you an example. A simple hierarchical network in which you spend the money on each level the same way, that's good enough for this, to show that you are at least reasonably competitive. That there's no, and I'm going to, on the next slide, I'm going to give you some caveats. We're assuming here, though, that your application's a bandwidth limited application. So we're not focusing at the moment on latency. Hierarchical networks, the latency is not going to be too bad anyway. I mean, that's what we use in data centers. But it is constructive because I'm telling you, it works to use a fat tree, right? It's a 4-level fat tree network. I'm just giving you a formula for choosing the channel capacities. Choose the channel capacities so that if you decided you're going to spend $10 million, you spend 2.5 million at each level and buy as much capacity as you can for that much money at each level. Does that make sense? I think that's constructive. I mean, it's not giving you all the details, but I'm kind of arguing the super low level details don't matter that much. As long as you can use whatever.
I missed the assumption. You're basically saying take equal port count switches at all levels. It's not like you're taking away that flexibility, or at least in the construction.
No. So, okay, first of all, it's not just about the switches, because it also depends on the cost of the wires, and longer wires cost more. Okay, at the moment that's kind of going away a bit, but longer wires cost more. So I want to give you the flexibility to decide what kind of switches you want, what kind of ports you want. No problem. I'm going to say, Ratul, you got $2.5 million. Buy the maximum amount of bandwidth you can. With what you pick the switches, you pick the top, whatever you want. You get this pile of money, but you just have to build a simple one level in the hierarchy for that much money, and everything else is up to you. Okay. So some caveats. So there is an assumption that you can buy, the amount of bandwidth you get is proportional to the amount of money you spend. In practice, this isn't really true, okay? There potentially you can get, by sometimes spending a little more, you can move up into a better technology that gives you a much bigger jump. Okay, that's true, fine. That's not perfect, but I think that affects things a little bit, but it's not a big deal. It also assumes that it's physically possible to spend the same amount of money on each level. Okay, that might not be true. It might be that you say, hey, I want to spend $2.5 million on the cables that run halfway across the data center, and then you find out, well, that you can't physically package them. And that's too bad. But on the other hand, anybody else building another network couldn't do that either. That turns out that doesn't affect the universality. And as I said before, it assumes that bandwidth and not latency limits performance. And there have been suggestions for networks, but the Jellyfish network and work that Michael's been involved in, where they're really trying to speed up applications where latency matters, and I'm not addressing that at all. So that's sort of an open problem about how to balance both latency and bandwidth. But again, we're talking about a pretty small constant factor when it comes to latency, because these hierarchical networks they do have small diameter. So I worked on this project with some people who are really experts at building data centers. And I said to them, look, I know you're not going to go out and build me a $100 million data center to see how it works. But I said, why don't we just look at some of the data centers that you guys have already built, or some other, let's just say that some anonymous company has built, and let's look at what the engineers actually spent on each level of the network and see, however they arrived at the decision, did they follow my rule? And so the guys who know about this said, okay, well, here's sort of what it costs today. There's a cost for each port. There's a cost for a direct attached copper line. It's cheaper than fiber, but it's got a limited length. The cost per port is a little bogus, because actually, if you look at the guts of a switch, the amount of hardware in there grows superlinearly with the number of ports. In fact, depending on how you measure it, it may actually be quadratic. So it's not really true that every port costs the same amount, independent of the radix of the switch. But for now, we just use that. And what they did was they looked at 2 generations of networks for me. And they found that, so this is actually, I guess this is now 6 years ago. They found that the first generation network, the amount of money they spent on the network was at the lowest level within the racks. They spent 6 times as much money as they did at the highest level in the network. And this is like a hierarchical network, like a factory. And what they found was that, well, the top level was a huge bottleneck. In the 2014 design, the ratio was 2 to 2 to 1. This is money spent. And I'm told that in the next design, this is closer to 1 to 1 to 1. So it's not that I had any influence on this at all. I think this was sort of what they started to learn as they were building these networks and running many applications. So that's it. The bottom line is, and this is something in all my distributed systems class, I always ask rhetorical questions to the class. I say, why do you think they did that? And some student will always raise their hand and say, money, okay? That's always the right answer, okay? So that's how I want you to think about comparing networks. Do it on the basis of actual dollars spent. Thanks. Yes?
So I have probably an open-ended question. So I think there was a discussion at the open problem session about like reconfigurable topologies.
Yeah.
I was wondering like if any of this theory sheds light on if there was like a moderate amount of reconfigurability or full reconfigurability, how do these results change? Right? I mean, there's been interest in that space. Well, presumably there's been interest in that space.
That's a good question. So again, I think it depends a lot on the details of how a network can be reconfigured. In principle, it seems like it should only help, because if you're trying to build a universal network, I had to show you one fixed topology and claim that for any application it will do reasonably well. I mean, yeah, it might be factor 4 slower or whatever, but if I could reconfigure the network, you might be able to do better. But I don't know exactly, there's a lot of different potential ways to reconfigure a network.
But sorry, I guess my thing is, are there like, what's the right theory pointers to look for?
So there has been a lot of work on reconfigurable networks. The problem is there's a whole bunch of different models on what you're allowed to do to reconfigure. And so you have to go look at the question?
Yeah. So I think we've had a similar problem when we propose kind of algorithms for the network, kind of routing schemes, in analyzing how efficient they are. So, for example, what we've been doing with when we try to analyze flow completion time, we use kind of these distribution of flow completion times that the big companies have advertised. Right. So, are you imagining that we'll have kind of the big companies release their cost structure to us, and we'll measure our systems based on these standards, or how can we agree? So, it seems that kind of an analysis of the specific topology is sensitive to the prices that you set. So the question is, how do you know what the prices are so you can measure your topology?
Well, that's a good question. I think my message is mainly aimed at the people who are building these big data centers, and they know the prices, and they're not, unfortunately, they don't release those prices. So there are sort of, from the point of view of being an algorithms designer, it's a little bit orthogonal. You're not going to get the prices of the network, and probably you're not going to get to choose what the network is anyway. But I do think that one approach you can take to analyzing, say, routing algorithms is that rather than I think it's okay to look at distributions, but you never really know how representative they are. The other thing you can do, though, is you can take the sort of emulation approach, and you can say, well, you know, can I do as well as something else? And say, you know, I don't know what's best, but at least I'm not too far off. I know that's kind of a vague, high-level thing, but it's just suggesting sometimes a different approach that instead of saying I can do it this fast, say, well, no matter what someone else does, I'm not that much slower. A competitive approach. Rachel?
Yeah, quickly after that, I think the prices being published in recent SIGCOMM papers are not that far off. That's all I'd say.
Oh, okay. Well, that's good to hear. Yeah. Okay, Nate.
So I love this. The notion of emulation, you said, was sort of based on doing the same amount of work in each time scale. So that seems like a very imprecise way of characterizing network performance. What happens if you try to be more precise? Like, you know, I might have some custom topology and custom routing scheme that provides all kinds of nice properties. And if I try to emulate that, the routing scheme may get very complicated. The tables may blow up. I may lose fault tolerance properties. Like, did Leslie look at those kinds of issues of how you? I'm sort of thinking of the network as a program, sort of transform one program to run.
Well, see, back then, first of all, we were assuming that there were no faults in the network and that it was totally static, but that you could design your own routing algorithm for it and build that into hardware. Today, you can do this kind of thing in a data center because you can use SDN, you know, pretty much to program whatever routing scheme you want on the network. But I'm not addressing things like if you want to do transcoding or something in the middle of the network, okay, that's outside the scope of this. We're looking at, we're only saying something about one basic functionality, which is route data, and where the bottleneck is throughput and not latency. We're making no further claims, and you're absolutely right. If you worried about functionality the network might perform that goes beyond that, I haven't said anything about that.
So given your caveat about how cost doesn't translate, you know, proportionally to bandwidth all the time, I'm just curious about the designs of these networks 5 years ago and in 2014. Did the designs change drastically, or it was just that the cost structures changed?
No, it was the designs that changed. It didn't have anything to do with sort of singularities in the price per bit as you spent more. They were just for whatever reason, they were just putting a lot less wires here, and that, you know, so that was a bottleneck. Yes, Rachel?
My sense of this change, I think, has been, I think there's been a change in the way applications are being deployed. I think the reason I suspect networks were built like that 5 years ago because there was a very clever layout of locality happening amongst applications. So you have essentially a set of servers co-located of one application. So naturally you wanted essentially more capacity at the lower levels of the tree. But then it became too limited. That applications got bigger and layout became a problem, and we started spreading applications throughout the data center. And that top basically then really started hurting. And so what now you want is basically not worrying about where applications sit. Thus you want, you know, these notions of higher bisection bandwidth.
Right. And Ratul, I think that reinforces the message, because it was sort of like you built a network and you had an idea of what the applications looked like, and then they changed.
No, I agree. I was just trying to explain where the trends are going without that deeper analysis that you were doing.
And as I said, I don't believe they did this because of any guidance from me. It happened anyway. Michael's getting nervous up here, so I better stop answering questions. But thank you very much.